Okay, hey folks, I want to record this quick video on Gibb's phase rule, which is going to describe how many phases that we can have in equilibrium. So if we take a look at our phase diagram here, the first concept that I want to introduce is this idea of degrees of freedom. And we'll note here that this is not quite the same meaning as our degrees of freedom when we talked about rotations or vibrations. So in this case, in a phase diagram, our degrees of freedom are pressure and temperature. So how can I change the pressure and maintain a phase, or how can I change the temperature and maintain a phase? We also have to think of the number of components, which, and so, sorry, by the way, degrees of freedom will have the letter F. Number of components will have the letter C. Let's make that F look a little bit better. So for a pure material, we'll have a C of 1. So most of the time, you've probably only seen or will only see a pure material phase diagram. But we can have multi-component phase diagrams. They get a little complicated, but all the same, we can do it. So Gibbs phase rule goes then as follows. F equals C minus P plus 2. So then the last thing to describe on here is P equals the number of phases at a given condition of pressure and temperature. So it's best to work through this with an example. So let's do that on this next slide. So here I have a fictitious pure material phase diagram. So C equals 1. And this is not a real phase diagram, as we'll see in a moment. And we have 5 different phases indicated here: alpha, beta, gamma, delta, epsilon. So now we're going to use Gibbs phase rule, F equals C minus P plus 2, to work out this degrees of freedom thing and what it means. Okay, so let's first work through. I'm actually going to have us work through D. I probably should have put the letters in a different order, but that's okay. So if I look at point D right now, I can see that that's going to describe, I was about to write 2, that's going to describe one phase, right? So that point is square right in the middle of phase alpha, so it's only describing one phase. And we know that there's only one component, so that means F equals, that's going to be 1 minus 1 plus 2, which equals 2. So what does that mean? Well, that means for point D, we can change the pressure, so that's 1 degree of freedom, or we can change the temperature, that's 2 degrees of freedom, and still maintain that phase alpha. Now, of course, as soon as we get to the phase boundary, that's another story. But within this shaded region, we have 2 degrees of freedom. We can move pressure independently, we can move temperature independently, and still maintain that phase. Okay, now let's look at point A. So point A is right on a phase boundary between alpha and delta. So that means that point is describing 2 phases that are in equilibrium. So now the calculation will go F equals 1 minus 2 plus 2, and that equals, so quick math, 1. Okay, so that 1 degree of freedom then for point A is P as a function of T. So in other words, I can't move pressure or temperature independently and maintain that equilibrium between the 2 phases. I have to change pressure and temperature simultaneously according to some state function. All right? So anytime we see a phase boundary, we should recognize that's 1 degree of freedom, and that 1 degree of freedom is our equation of state describing P of T. Okay, I think I said state function. I really meant to say equation of state. Okay, so like ideal gas law, for example, or the van der Waal equation, or something like that. Okay, now if I look at point B, I can see that that's a triple point, right? There's 3 phases in equilibrium right there. So P equals 3, And so the calculation now goes 1 minus 3 plus 2, and that equals 0. So 0 degrees of freedom at a triple point means if you want to maintain the triple point, you cannot change pressure, nor can you change temperature. It is locked in. And then finally, if I look at point C, if such a point could exist, we can see there's 1, 2, 3, 4 phases all shared at that same point. So P equals 4. So now I can say F equals 1 minus 4 plus 2, and that gives me -1. Well, that does not exist. I can't have -1 degrees of freedom. So in other words, 4 phases cannot exist in equilibrium if C equals 1. So for a pure material, we can't have 4 phases in equilibrium. Now, if we had a phase diagram of a mixture, and we'll get into that soon, so where the C is greater than 1, then you might imagine we can have 4 phases, or even in some cases 5 phases in equilibrium. But it's important to recognize for a pure material, we can only have 3 phases in equilibrium. Okay, that's all I wanted to say about that. I'll see you in the next video.